Hello, everyone. My name is Wyatt Reese, and I'll be presenting my work with Daniel Atelier on our survey of deep learning for inverse kinematics. So despite advancements in autonomy, robotic manipulators continue to be deployed with manual control mechanisms, where an operator either specifies a goal position and orientation or velocity of the end effector. However, low-level control of robots is done by actuating individual joints. So we must put a burden on the control system to translate end effector positions and velocities into joint positions and velocities. This translation is known as inverse kinematics, or IK. There are many aspects of this problem that make it difficult to solve. It is a nonlinear problem. A robot with more than 6 joints is redundant, meaning that it may have an infinite number of IK solutions. Traditional methods suffer from high computational complexity. Certain types of robots do not have closed-form analytical solutions. There may be human constraints that play into choosing a redundant solution, but they are difficult to formalize. And certain joint positions can leave the robot in a singularity, making it unable to move in certain directions. One of the earliest approaches in using deep learning for solving IK was found in 2004. This laid a lot of groundwork for how these types of networks can be designed, but lacked in ecological validity, as robots with 3 joints or a 3 degree of freedom robot is not common in the industry, as it can only control for position. The architecture was relatively simple here. Used 3 input units representing the position of the end effector, had 1 hidden layer, and 3 output units that represented the joint angles. The study also laid out how to generate training data by moving the robot's joints through predetermined trajectories and calculating the end effector position at given intervals. This was later expanded to use a 6 degree of freedom robot, or a robot with 6 joints, and one with no closed-form analytical solution. It also compared multiple architectures' performance by changing how the orientation of the end effector is represented by the model. You can use a rotation matrix to represent this orientation. You can use Euler angles or an axis angle representation. Aside from that, the architectures were identical. And it turned out that although all of the models had relatively high error, the transformation matrix representation performed the best. The next major step came in introducing recurrent neural networks. In particular, this work introduced 3 independent parallel Elman networks, which are a type of recurrent neural network capable of providing state space representations for dynamic systems. And so in order to calculate IK, each of the 3 networks were queried simultaneously, and then the solutions were checked for accuracy, and the one with the best accuracy was chosen. Each of the 3 networks had very similar architectures, differing in the number of hidden layer units, and also having unique training data. To evaluate the performance of these networks, the mean squared error of the end effector position was taken, and independently, each one did not perform so well, but when used in parallel, performed much better. Additionally, the reliability was measured to be very high, nearly 100%. Also expanding upon this was the avoidance of singularities. So unfortunately in this paper, the authors omitted any architecture details, but did show through simulation that you can identify volumes for the robot to avoid so that it will not enter a singular state. And as most of the IK research is focused on robotics, it does have an application in computer graphics, in particular, creating realistic motion controllers for animated characters. While these do not typically share the same constraints as robotic applications, we can still gain some valuable insight. One interesting study in this domain was the use of neuroevolution of augmenting topologies algorithm to alter the structure of a convolutional neural network as it trains. It does this by adding connections or adding units. And this implementation was able to control a real physical simulation of a human character, such that they could walk without falling over. Towards a similar purpose, we also saw a convolutional neural network that was able to develop joint trajectories for an animated human to walk. It did this by utilizing a convolutional autoencoder over the temporal domain with a max pooling layer and an ReLU activation function. Also, very recently, reinforcement learning has gained much popularity, especially in robotics. Reinforcement learning works by learning some policy, which determines how an agent should act in its environment. However, this often requires processing very high-dimensional features of the environment. So we can use deep learning to learn this policy. We found 2 particular studies that are interesting in this case. However, neither of them actually calculate IK, but they do show that very complex tasks can be learned through this method. So while the recent boom in deep learning has had a positive impact on IK, there's still a lot of work to be done. In particular, some of the open questions that we have identified are, can we use deep reinforcement learning to solve IK? Can deep learning be used for arbitrary robots IK? And how might the architecture differ? And can we use the techniques studied in the context of animation for robots? Thank you.